Doug Moen.
Hi, Doug.
And welcome to my open source software project. It's last time I was here. Okay, so basically, yeah. So those are like 3D printed models that I created with my software, and the models are actually sitting right there. And maybe I'll pass them around at some point. So the project is called Curv, and so it's basically, so it's a functional programming language. It's used for 2D and 3D solid modeling, and you can obviously 3D print things. It's intended to be used for live coding and generative art. It's supposed to be used by artists, designers, and 3D printer enthusiasts. And it's kind of an ongoing research project. I've been working on it for years, and it's still only at 0.4. But the like it's sort of like part of it is like programming language design. Part of it is like creating this weird geometry rendering engine, and then there's user interface stuff that I'll talk about. The goal is to make it like simple, easy, and powerful. So I'm trying to make like the most powerful 3D solid modeling system ever created with the best programming language ever, and that sort of thing. It's a hobby project, right? So, and it's on GitHub. I did a presentation at StarCon in January. So I actually stole some slides out of that and wrote a script. Okay, so there's an example of creative coding. So that's an animation. It's not working very well, but it's supposed to do. Anyway, so creative coding is the act of writing a computer program to make art. It's fun, it's interesting, and it lets you do things that are hard to do in any other artistic medium. So this is like kind of like the core point of the software. So creative coding is a fun and rewarding way to learn computer programming. You can write simple programs and get immediate visual feedback, and even bugs lead to interesting results, which is why I chose this particular domain. It's just like partly I wanted to invent a programming language, but I also wanted it to be fun to use. And so writing short programs and getting like cool animations out of it that just seemed like the best. So there's a program, and there's the thing that happens on the screen when you run it. This is also used. And then part of this is that I wanted to make 3D printed art. So there's one of my models, and there's the source code. So the concept behind generative art is that instead of like having conventional artistic skills, drawing things and so forth, you just write a computer program and it makes art for you. So that's kind of where I'm coming from. I understand math, but I can't actually draw figures, so but I can do art this way, which makes me happy. So part of the idea of generative art is that you can define parameters that control what program is going to generate. You can manipulate those parameters to explore the parameter space. So that's what I'm supposed to do next. So here we're going into live demo mode.
If you slide the window, usually people are sliding the windows, and you have many windows.
Okay, so that actually is displaying now. So there's one window, I've got the source code, the other window I got the model. Sorry, what?
Can you make the font bigger?
Sure.
Thank you.
Well, anyway. Looks like it's one or the other.
That doesn't need to be bigger.
so, yeah. All right, so I've got two parameters in there, A and B. You can see the parameters are defined at the top of the screen. This is something that's new since the last time I demoed. So if I just drag these sliders, then I get to explore my parameter space. And those cool things. So this is, so that's the basic concept of parametric design. You twiddle parameters and you figure out what numbers you want to make it look good. What do we got next here? Slideshow. So this is basically, so the Curve project started when I discovered the OpenSCAD program. So OpenSCAD is sort of what you see at the top there. It's a 3D modeling program with an associated programming language, and it's basically it's basically a simple declarative language where you can create shapes like cubes and spheres and perform Boolean operations and so on. And you can make 3D objects and then you can 3D print them. One of the things I discovered about OpenSCAD is that it's not very good at handling curve shapes, and it's really designed for CAD. So if you want to do like wild artistic stuff like what I just showed you, then it becomes extremely difficult. Then the other project that I found around a little later is on the bottom half of the screen, and that is shadertoy.com, and that is a community website where people create basically GPU fragment shaders that produce three-dimensional scenes, and you can post them to ShaderToy and you share them with the world. And there's this nice little interface there. There's source code on one side and the output on the other side, and it's kind of like OpenSCAD except completely different. You can do much more artistic looking things in ShaderToy, but it's only for creating flat images. You can't. There's no 3D model there. You can't print it. So the genesis of the project was, what if I use the rendering engine in ShaderToy, and then made a system kind of like OpenSCAD, except that you can do everything you can do in ShaderToy. So, and which requires compiling, designing a language where you can define 3D shapes and then compiling into GPU fragment shaders and executing those programs on the GPU. So that's what I actually demonstrated the first time I was here in 2017. And then I've sort of since done a lot more things. I think in 3D print things now. So the way now the problem with ShaderToy is that the programs that you write are extremely low level and complicated. They're written in GLSL, which is a very low level language that runs on a GPU. And so I wanted, so this curve is supposed to be simple and easy, right? So to make it simple and easy, you don't want to have to write like 40 lines of code to produce a sphere. You want to be just type sphere. So on the left side of the screen, sphere 1 is the program, and then it produces a sphere as an output. So that's the high level interface to Curve. The low level interface to Curve is an API called MakeShape, where you actually define what is a sphere. And in geometry, a sphere is defined as an equation: x squared plus y squared plus z squared equals r squared. And if you so x squared plus y squared plus z squared is actually the magnitude of the vector x, y, z. And then you take the square root of if you take the square root of x squared plus y squared plus z squared, then you get the magnitude of the vector x, y, z. So that's what this is right here. And if we subtract r, then that's going to be equal to 0 at the surface of the sphere. So that's sort of like the underlying mathematical magic that underlies how Curve models 3D shapes. So basically you take the mathematical equation for a 3D object and it magically, does things. Okay. So I could go into more details, but I'd like to get this going. Okay, so here's where we go into underlying demo. So basically what I want to show here is like how you would like basically write some code from scratch write a curve program from scratch in high-level interface. So that means I've got to go over here. And okay, so first of all, I'll just type box. Except I'm in DI, aren't I? Okay, never mind. DI word. So I typed in, okay, the program I typed in is box. So the 3 letters, that's the entire program, and it gives you a box. Okay, so that's sort of like the equivalent hello world in Curve. So next thing is I'm going to give box a parameter. So 115, and what that does is that makes it into a cuboid with, the dimensions 1 and 1 on the x and y axis and 5 on the z axis. Z axis is vertical because that's how 3D printers work. So the next thing I'm going to do is keep the color. Okay, so in Curve, okay, so I'm going to type color red. So this is like a Unix pipeline. So like it's deliberately modeled on like how the shell works. So basically you have commands and you pipe them together. That's kind of like the essence of high-level Curve programming. So I took a box and I piped it with color red, and I have a red box. So next thing I want to do is I want to make this parametric. So I have a parametric keyword, and make a parameter called C, and I'm going to bind that to a color picker, and the default value is red, and then so what happens now is I just added a color picker control to the top of the screen, and so I can modify the color. It doesn't work because I forgot to plug the parameter C into the program. That's why it's not working. There we go. So now I have this nice blue green box. So next thing I want to show you is the twist operator, which is kind of cool. So basically Curve has a lot of different operations that you can perform on shapes. So there's like there's Boolean operations like meeting and intersection, and then there are transformations which like do linear translations like move and rotate, or you can do like plastic deformations like the one I'm just about to show you. So the twist operator is, I like the twist operator. Okay, so the way this works is that the argument to twist is basically the rate of change, the number of degrees per unit distance along the z-axis. So what that's going to do is twist it 90 degrees over a distance of over a bit. That, yeah. Much more contrast. Yeah, okay, that's good. So I twisted it.
What makes it go in the Z axis there? Why just twist on the Z, not the next one?
That's just the default axis that's used by the twist operator.
Okay.
The twist only twists along the Z axis, so if you want to twist along another axis, you have to rotate it, your object, so that the twist axis is Z, and then rotate it back. That's just the way it works right now. I could have had a lot more parameters, but I just decided to make twist simple like that. Okay, yeah, so let's make the twist angle into the parameter. So I'm going to add another parameter called angle. And the picker is going to be a slider that goes from 0 to 720 equals to 90. Okay, so now I've got an angle, and yeah, here, okay. So I can do that, right? So what's actually happening here is that okay, so this program is basically compiled into a GPU shader, and that program is executing 60 frames a second according to my FPS counter. So that's why when I change one of those parameters, it reacts instantly because it's actually re-executing the program 60 frames a second. Yeah, there's a little bit more I wanted to do with this demo. Okay, so the next thing I want to do is I want to use the bend operator. So the bend operator is another operator that that uses the Z-axis, creates the Z-axis in a magic way. So I have to first rotate this thing into place before I can use the bend operator the way I want it to. So I'm going to rotate it 90 degrees along the Y-axis. Then I'm going to use the bend operator. And bend has a bunch of parameters, but I'm just going to let them all default. So now I got this. So So that's my model. Okay, so that's basically what curve programming looks like. It's when you're programming, when you're using that high level interface. So there's the program. It's like beeline or something like that. So let's see. Let's see what else we can do here. Okay, so how am I doing for time? I got more time. Okay, good. I just want to show you a little bit more about Curv then, in action. shell window where I wrote the curve from. So I'm just going to try and got many examples for you right now. And I want to show off a few more capabilities. So one of the things that Curv does well is that it can represent the curve representation of the shapes can represent fractals. So I will show you the Mandelbrot set. There we go. So Curv does 2D and 3D, so this is a 3D model. And I just wanted to basically demonstrate that. So with a conventional CAD program like OpenSCAD or one of those CAD programs that use splines, the memory requirements go up, with the complexity of the object that you're displaying. So if you've got something like this, and it's made out of, polygons or whatever, you're not going to be able to zoom in like this without occupying megabytes or gigabytes of memory or whatever. So, but this Mandelbrot program is very simple. It's just like basically a 20-line loop, and it just calculates. What it's really doing is just basically calculating the color in each pixel. The only reason that I can't zoom in infinitely is because I'm using floating point, and so at some point I should run into the limits of. There we are. Yeah, so I'm running into limits of floating point resolution right there. I'm using 32-bit floating point. But there we go. Now that's a two-dimensional fractal. So I'll just show you a couple more, just so that yeah, okay. So there's the classic Menger cube. Yeah, I'm also going to show you one more, which is now the Mandelbrot is a three-dimensional object that was originally designed to be the three-dimensional generalization of the Mandelbrot set. The cool thing, this thing, theoretically you should be able to zoom into it. I have a limitation in my viewing software right now, so if I zoom in too far, then I end up in the inside of the object. But there's a lot of detail there, and it's something I want to explore more in the future. Now, another thing that you can do with Curv is you can use noise to generate, sort of like natural-looking imagery, I guess. So here's the specific technique is usually called fractal noise. Okay, this is a two-dimensional model, and it's a smoke simulation using fractal noise. So it's just from a modeling point of view, this is just basically a circle, and I've just painted the circle with the smoke pattern, and I'm animating it. Now, I can also use fractal noise to do things, to create three-dimensional shapes. So there's this one. So this is a sphere, and I'm perturbing the surface of the sphere using fractal noise. So this is what happens as I move the slider. I guess this has an explosion effect. So anyway, so I think I'm trying to demonstrate that that Curv is actually a very powerful modeling tool. yes.
So now when you do that, is that deterministic or is that random every time you zoom out?
No, it's completely deterministic. Basically, so Curv is a pure functional language, so I don't have, like the random numbers are produced by hashing X, Y, Z coordinates. And if I wanted to get different versions of this, then I have to basically get a source of randomness from outside the program and mix it into the hash. But I'm not doing that.
So was the smoke repetitive then, or?
No, the smoke's not repetitive, it just keeps, it always starts at the same spot, so that's spot in the animation done. Yeah, so basically, yeah, in GPU programming, yeah, random numbers are generated by hashing, that's just the way it is.
Can we see the code for this?
Oh, of course you can. Okay, so there's a fair bit of code there. Let's see what I got. Okay, right at the bottom, I've got so the last line of code, I'm making a sphere, and I'm typing that into displace, and then I'm typing that into Lipschitz 3, which is magic, and then I'm typing that into color to give that fire pattern. And then all those operators are defined. So fire is basically a function that takes I and maps it onto, I is basically a number between 0 and 1, and it's basically a color map. I underscore fractal is an intensity field, which basically maps three-dimensional, like X, Y, Z coordinates onto intensity values.
What's Lipschitz?
It's magic. Okay, so the Lipschitz is basically an artifact of the way that my rendering algorithm currently works. So this is kind of a simplified variant of ray tracing called sphere tracing. So sphere tracing is an algorithm for taking a sine distance field, which is the actual representation of shapes, and basically sending rays through the distance field to find the boundary of the shape. So the sphere tracing algorithm has a limitation. It places constraints on how fast the distance function can change. The technical mathematical limitation is that the function must be Lipschitz 1 continuous. So this particular field that I'm producing is not Lipschitz 1 continuous, it's Lipschitz 3 continuous, so I have to apply a Lipschitz compensation factor in order to make the sphere tracing work. And this is when you get into with the high-level library, you mostly don't have to worry about this. But when you start to write low-level code, then you're creating these distance functions. You don't know how they're going to behave. Like you don't want to spend a lot of time doing mathematical proofs and so on. So what you do instead is you just write some code, see what happens, and if it's not Lipschitz 1, then you just apply a compensation factor, and everything's fine. This is what happens when you use the low-level programming interface. So there's a lot of this. Okay, so I'll give you a little bit of information about what this code is doing. So right here, so that hash function is basically generating a random number. So I'm taking a value n and I'm hashing it as a number between 0 and 1. That's how I make random numbers. That's basically the visual equivalent of white noise. It's uniformly distributed random numbers. And then this next function is called noise. And this is another kind of noise which is called value noise. And if you plot what value noise looks like on a well, if you basically create an image of what that noise looks like, white noise is basically it's very spiky. It has lots of high frequency components. It basically looks like, you know, I don't know, old-fashioned television static. Whereas value noise changes gradually. It's more it has more useful properties. It's still not equally aesthetic, but at least it's more useful as a building block. And then there's somewhere in here there's going to be, oh yeah, there we are. So this one is taking the noise function, and so basically the noise function there, the value noise function, has a characteristic visual frequency. And what fractal noise is you take you mix together several different octaves of value noise. You blend them together so you have, you know, here I'm iterating in I think, well, no, I'm not actually using a loop, I'm just doing it 3 times with different scaling factors. So I'm basically taking 3 different octaves of value noise, blending them together, and that's how you get fractal noise, which has much nicer looking visual characteristics. And that's probably you'll have. I don't.
What does
can't.
LERP stand for?
What?
What does LERP stand for?
LERP is linear interpolation. So yeah, it gets used a lot in this kind of programming. So yeah, there's like 3 arguments. You know, A and B, and then so basically you're doing a linear interpolation between 2 values, A and B, and then there's a third argument which is basically between 0 and 1, and it tells you, 0 gives you A and 1 gives you B, and other numbers give you other values. Yeah, and I didn't write most of that code, so my knowledge of how it works is limited to basically what I just told you. I copied this off the internet, of course.
We see the smoke. We see the smoke script.
Yeah. Okay. The smoke script is actually very similar. It uses the same technology, but it was written by a different person than the person who wrote Kaboom. So there's differences. So there's my hash function. It's called random in this case, and I borrowed the code from Patricio Gonzalez, who I'm pretty sure borrowed it from other people. So there's the value noise, and it's written in a slightly different style, but it's basically the same concept. And then this is my fractal noise. Fractal noise is sometimes called fractal Brownian motion, so that's why it's called FBM. And then instead, so in this one I'm actually looping 5 times to generate the 5 different octaves of value noise that are being blended together. And then those are the noise primitives. And then smoke calls FBM and LERP a whole bunch of times. And I don't actually know what it's doing, but it looks really nice. So again, that one I actually have no idea how that code was written. It's full of magic numbers, and it's just mysterious. But I saw it on the internet, and it looked so cool that I had to, try it out at Curv. And then, yeah, and then smoke. But what I did, so my contribution here was really to package smoke up into basically an animated color function. So smoke takes 4 arguments, x, y, z, in time, and it returns the value, basically a color, the color of what the smoke looks like at that x, y, z coordinate at that time. So it's a 3-dimensional it's three-dimensional smoke, but I think is it three-dimensional smoke? No, it's not. It's only two-dimensional smoke. The Z argument is ignored, but it doesn't matter because I'm doing 2D. That's what happens. Yeah, but the color primitive takes a color function. You take a color function as an argument, which has this interface. So what I did is I just took Patricio's code and I packaged it up in the interface that Curv understands. That you can plug into the high-level color function. So one of my so one of the things I want to do in the future is to sort of make a generalized noise library that packages all these techniques up in a nice way, so that you can have a whole bunch of like high-level noise primitives that you can use without understanding how all this stuff works. That partly depends on me understanding how noise functions work. So it's all my future to-do list item. So it's already 10 minutes to 9. What time do I have to stop? 9. Okay. So what I'm going to do is I'm just going to quickly go over some slides that I prepared about what's going to happen in the future with Curv, because this is like an ongoing project, as I mentioned. All right. So at this point, there are the Curv project has basically 2 main developers, me and there's Sebastian. And we've got a nice division of responsibility. So my role is to make Curv more powerful, and Sebastian's Curv is to make it easier to use and more accessible. So he's actually working on a separate project called Curelet, which uses Curv as a dependency, and what he's doing is making it run in the web browser, and I'm basically supporting him on that, and also working on my own projects to make Curv more powerful. So I'll start off with what I want to do. I want to make Curv more powerful, so I want to support a wider range of 3D modeling techniques than what I currently do. And I want to support import of image files, voxel files, and triangle meshes. I want to support, so I can do, I want to support advanced 3D printing. So I do have the ability to make color fields, so I can print like full color 3D images. But Shapeways just got a Stratasys J750 3D printer, which does, which basically is a multi-material printer. You can control, and on per voxel level, you can print solid objects right at each voxel. You can independently control whether it's rigid or flexible, and you can control the color using RGB, or actually cyan, magenta, yellow, black, and white. And you can also control the transparency on a per voxel level. So I can't actually make, so what I'm, in order to be able to fully exploit that printer, I need to be able to create models where you can have translucency and basically multiple materials, like, vary the level of, flexibility on a per voxel basis. So that's something that I'd like to try in the future. I think you can do really cool things with that printer, but the question is how you create the models, right? So I can create the models with Curv if I just extend them like that. Then I have requests from my users. So I'm more focused on 3D printing. What they want to do is they want, I advertise Curv as an art program, so I have people who want better aesthetics. Who would have predicted that, right? But they, so Philip wants beautiful 3D rendering with lighting, shadows, materials, and full camera control. And he's actually a pending pull request where he's implemented some of that, and it's not integrated yet because of some technical issues. Sebastian wants to be able to duplicate anything he sees on shadertoy.com using Curv. And there's another guy whose name I can't remember who wants to do generalized ray tracing. But he's not offering to write code, so his request is at the bottom. That's not going to happen as fast. Philip's actually writing code, and Sebastian's actually writing code. Okay, so how do I accomplish this? So I want to make Curv is partly an experiment in programming language design, so I naturally have ideas now to make Curv language more powerful and expressive in ways that will help me to make models, basically make the library KPIs more expressive, so I can do more things. I want to expand it, shape Curv, I mentioned the noise library as an example. And one of the limitations of function representation I'm using is that some function representations are just too slow. You know, I showed the stuff that I showed you is mostly rendering at 30 frames at 60 frames per second. But if it's rendering at 5 seconds per frame, then you've lost your ability to animate anything. So some of the things I want to render, I know, you can write a function representation absolutely anything you can imagine, but it's not guaranteed to run fast, right? That's the problem, is speed. So to make certain types of models run faster, I actually want to use alternate shape representations. I'm still going to use sign distance fields, but instead of using a function representation, I want to use data structure representations. Hello?
Why do you care about speed if you're just generating a static content?
Because when I'm defining parameters, I'm pulling the slider across the screen to see how the changing the parameter affects my shape. I'm doing animation in real time. And if it takes like a minute to animate, just to render one frame, then I can't use the sliders.
So if I just want to generate a function, something with a function draws.
I mean, yeah, you can still use Curv. You just can't use that particular feature, right? You can make a function representation run really slowly, but it might take an arbitrary amount of time before you actually see what it looks like on the screen, and then you can export it to STL and 3D print it. All of that is possible. It's just it's not the user experience that I want.
3D printing is where the latency is.
Yes, but I want to be able to preview my shapes on the screen with real-time animation, right? And in order to do that,
I think your software's great already, so that's all.
yeah, but I'm not satisfied, right? So I'm thinking about performance. So I'm thinking about alternate shape representations using data structure representations and sign distance field. One of those is going to be voxel arrays, and there's a bunch of other, there's all sorts of other possibilities, and there's all sorts of research papers. And then the other thing that I want to do is a high-performance GPU rendering system. So right now, I compile the entire program into a single fragment shader, and that has limitations. So I want to, there's alternate ways of doing it, where you build a pipeline of shaders, and you get more parallelism because of, GPU magic, whatever. And so the main problem, so I know how to code it. The main problem I have is actually shader pipelines don't currently run in WebGL, the web browser. And so we're waiting for a new standard called WebGPU that runs in a web browser and supports shader pipelines, but the standard actually is still under development. Anyway, but this is a multi-year project, right? I've been working on this since 2016. I'm not even halfway through. So by the time WebGPU is it's available in browsers right now, but you have to enable the feature. Basically go into developer mode and turn the feature on, and I don't know, maybe like next year, this will be generally available, I hope.
OpenSCAD, is Tinkercad better or which
Yeah,
one's better?
Tinkercad is, okay, so I have successfully taught 12-year-old kids how to use Tinkercad in like a minute. Tinkercad is extremely easy to use. There's no programming language that you have to learn. OpenSCAD is a programming language, so there's this learning curve where you have to learn how to write code before you can actually do it, right? So, if you want easy to use Tinkercad, is like the first thing I recommend. That's sort of like, that's your entry point into a 3D model, and then you can start using more sophisticated tools that are more difficult, that are more powerful. So anyway, so Sebastian's job is to make Curve easier to use and more accessible. So right now, we don't distribute binaries. You have to compile it, download the code from GitHub, and compile it yourself. And we're going to have a web UI. So you can just basically go to editor.curve3d.org, and you will be and you'll just be able to instantly start writing Curve code, and it will render in your web browser. That is fundamentally what Sebastian is working on. And then we also want to have a web community where you can, share your project with other people, like GitHub during the Curve Hub, or similar to how ShaderToy.com works, where you basically have a whole bunch of users. And so the obvious way, of course, is to do it like centralized, but there's apparently other ways of doing things. But we want a web UI, we want a web community, and then we want. So I'm claiming that I want Curve to be usable by artists and designers, but it's a programming language, a text-based programming language, right? So that there's a little bit of a problem there, because most artists I know would not actually be able to use Curve in its current form. So that's the whole problem area that Sebastian and I want to solve. So basically, the idea is this progressive disclosure user interface, where you start with doing things that are very easy, and if you progress to more and more difficult levels that are harder to use but more powerful, and it's a progression. You don't jump directly into a text editor and expect where to go. So in Sebastian's UI, you go to the Curve website, and it starts off by showing you a bunch of example programs, like a grid of tiles with different types of models you can create in Curve. You click on one of those, and then you see that close up, and there's sliders, built-in parameters that are predefined parameters and sliders, and you can basically customize the model to look the way you want, and maybe at that point you 3D print it and you're done, or maybe you want to look at the source code. So you open the source code, and then you can puzzle it out and maybe make changes to it and see what happens when you make changes. Maybe you want to clone the example, make your own project and start modifying the source code, or create a new project from scratch. And then, so initially, that's all going to work in terms of a text-based interface, but we want to make Curve into a visual programming language where you can basically graphically edit source code somehow. There's some unknowns there. We don't really completely have the design for a visual editor yet. This is Sebastian's project plan. This is a multi-year project plan, because like me, he's doing this like as a spare time hobby. So version 1, that's going to be coming up first, and that's basically a text-based integrated development environment that runs it'll have sliders like I showed you, but it won't be fundamentally different from what Curve is today, except it's running in weapons. And then version 1.5 is concept of a sketch, where you have I don't know, I haven't seen it yet. Basically it's kind of like literate programming where you basically have documentation and codes with interwoven into a doc, into a unified document. That's kind of what he's aiming for there. And then version 2 is where we replace the text editor with a structural tree-based editor. And it says right there, uncharted territory, because a lot of the UI design has to be done for that. Version 2.5, but he still wants it to basically be isomorphic with the text representation that I showed you, except that you're not editing text, you're editing tree. That's all I can really tell you about his vision. Version 2.5, this is where, so we talked about how can we make Curv more like Tinkercad, right? Because Tinkercad's easy to use. So version 2.5 is where we try to make Curv look more like Tinkercad, where basically you can directly manipulate the 3D object on the screen using the mouse, and there will be like control points that you can drag. I don't know how this is going to work, but I have ideas, but the big picture, I don't know. And then version 3 is something that an idea that I'm trying to sell Sebastian on. And it's basically, I want Curv to basically be more of a visual programming language where instead of basically text, it's more like, a diagram-based visual programming language. And so the problem, we both looked at a whole bunch of different node-based visual programming languages, and we uniformly hate all the ones that we looked at so far. So the challenge here will be finding something that we are personally comfortable with. And the problem is it looks gorgeous on the screen, but the actual user interface for creating code turns out to be tremendously clumsy. So that's kind of like the problem. One solution I have for that is basically that there's an abstract tree which represents the code, and there's a text view of that tree, and there's a diagram view of the tree. You can just flip back and forth, and it's the same code in two different views. Now that's an idea that I have. And then I'm going to also do research in different ways to create diagrams that you see, you might model them like better than stuff that you've seen already. So, but this is version that's speculative because we haven't actually found a design that we actually like. Yeah, so then, in order for Sebastian to do his work, he needs some support from me. So the first thing I'm doing right now is I'm actually porting the Curv to WebAssembly, which turns out to be actually worse than porting it to Windows. But that's because WebAssembly is a very immature technology, and it's not really, people are using it, but it's not mature. There's a lot of things that are very rough. And the other thing that we're going to eventually want is an incremental compiler, and similar to, I think it's going to be similar to what are found in like Visual Studio, that sort of thing, where you have this incremental compiler that basically takes commands that are passed to using Microsoft Language Server Protocol, and basically the incremental compiler maintains a tree of source, and it gets basically queries, it gets sent tree queries, and it also gets sent requests to make changes to the tree, and it changes the tree and then incrementally recompiles just the parts of it that have been changed, and it gives back results. It's anyway, that's a big project, and I don't actually, I have no idea what I'm getting into with that. But it's part of our project plan, right? So happen eventually, and then we also want to have this web community. And so one of my ideas is that we should have a package manager, and you should be able to reference other people's libraries using URLs. So package reference using URLs, and then what servers are the URLs pointing to, well, I've already registered the domain curve3d.org, but then the question is, if we put everything on curve3d.org, then Sebastian and I are paying for all the server costs. So then, I've heard of this magic thing called IPFS, and maybe it would, provide, could be part of the solution to this problem, but I don't have, a really concrete idea of how it would work or how well it would work. And that's the end of the presentation. So I guess if people have any more questions right now.
Is this running only on the GPU?
Is it running on what?
Only on GPU? You run it?
Yeah, well, when it's rendered on the screen, it's using a GPU. And when I render a 3D shape as an STL file, I'm actually using a CPU for that. Because converting side distance fields into triangle meshes using a GPU is really difficult, and I'm using other people's source code which runs on the CPU. So I'm using both, depending on what you're trying to do. So, okay. All right. Yeah. Oh.
So are there artists using Curve right now? And if so, how many?
Yeah. Behold the splendor of my art. It's sitting at the front table here. So basically, at this point, so the answer is that, yeah, I have users. But in order to use Curve, you have to be sophisticated enough to clone a Git repository and type make install, and submit issues if it doesn't compile correctly, and so forth. So this creates a fairly high barrier to use. So the only people using it right now are actually software developers who have artistic inclinations.
Right, but so let's say that somebody made packages for it. It seems like it's iterative, and you can do high-level things like Sphere 1 that I'm not sure that I believe you when you say that artists couldn't use it even with its current text editor. I guess.
Oh, well, yes, they can. The thing is, okay, so my wife is an artist, and I've spent a lot of time talking to, over the last number of years, I've talked to a lot of different artists who live in town, and I think, I don't know, I'd say maybe 1% of the people I've talked to, like just attending art gallery openings and all this kind of stuff, would actually have the sophistication to do Curve programming. Less than 1%, I would say.
But I mean, when I think about art, like less than 1% are doing bookbinding, and less than 1% are working in glass, and
Yeah.
I mean, the art is, quote, art is a fractured community to start with. So there'd be
Yeah.
the Curvists, or the Curvies.
Okay, I'll show you some art that wasn't created by me. Okay. Okay. So I think this guy's like in Austria or something like that. Anyway, so he did this, and like when he posted this, like I was like totally impressed that you could actually do wood grain in Curve. I had no idea it was possible, but there it is, right? It actually looks okay, cool. So then, I mean, this is based on the same kind of fractal noise stuff, I assume. I mean, I've looked at his code. I don't fully understand it, but you know, I would call that art. And and the people who are contributing, some of the people contributing right now are definitely have artistic ambitions. Like Sebastian has, he's basically he's sort of like a he has like he runs a computer graphics company, and like, you know, does technical stuff for clients, but then and he's a web designer, but he also wants to, you know, like do really cool looking, you know, pure art projects as well using Curv. And then and Philip is clearly focused on creating really aesthetic looking things, because he submitted this pull request that, you know, adds this really gorgeous, you know, shader that like rendering system that renders objects using realistic, like multiple light sources with colors. You can arrange them in 3D space, and it casts shadows which look realistic. Maybe you can control the optical properties of the surfaces. Like you can make something look metallic, or you can make it like matte, or, you know. And this is all in his pull request, right? And it looks wonderful. It is like, you know, so he's clearly got aesthetic things that he wants to do with Curv. So we can call him an artist as well. But he's obviously but he submitted C++ code, right? So he's an artist who can run C++.
You mentioned STL that runs
Yeah.
on the CPU. So
Yeah.
how you switch? It's a compiling option. What code runs on GPU and one on CPU?
Okay, so Curv is fundamentally a command line program. So if I want to export finial.curv to STL, I type curv-o finial.stl space finial.curv, and it will generate an STL file called finial.stl. And then you have an STL file, now you can 3D print it. And the way that works is that I actually take the distance function. The distance function takes maps x, y, and z onto a signed distance value, which is the distance from that point to the nearest surface of the 3D object. That is the fundamental representation of shapes and geometry in Curv. So to do XTL export, I iteratively call that distance function on every point in a three-dimensional voxel grid. I just basically, I know the bounding box of the shape, so I form a voxel grid around, you know, I partition that bounding box into a voxel grid. I calculate the distance function at every point in the voxel grid, and then I hand out this array of voxels to a third-party open source software library, which then magically hands me back a list of triangles. So that's how STL export works. And there's there's a number of different open source software packages that will do this, and with different levels of performance and different levels of quality in the output. So over time, I want to experiment with multiple different libraries to see if I can, you know, basically find something that has you know, a good balance of speed and output quality. But I got something that works right now. It's just, it's not. I don't think it's ideal. I think I can do better.
Were these models done using that method?
Can't hear you.
Were these models that you did here done using that method?
Yeah. So the limitation of the algorithm I'm using right now is actually called marching cubes, and the limitation of that algorithm is that it doesn't do a good job on sharp edges, which is fine because I don't actually try to sharp edges. It's called Curv because I want to do, like, you know, smooth organic shapes. But it's you have to basically crank up the resolution of the voxel grid in order to get sharp edges rendered correctly. So that's not ideal because the bigger the more voxels the bigger the voxel grid is, the slower the rendering is. So there are other algorithms that do automatic edge detection and automatic vertex detection in the signed distance field. And these algorithms are more complicated, The most popular one is called dual contouring, and it's very popular. It's used in video. It's a perfect algorithm in video games. The problem is dual contouring produces triangle meshes that are defective, and when you hand those defective meshes to a 3D printing program, it'll say your STL file is damaged and you want me to attempt to repair it, right? So that's not great, and then the repair process might go completely screwy. So you don't want these defective meshes. So then you want an algorithm that will produce defect-free meshes and also do edge detection. And I'm talking about it's called Sharp ISO. It's on GitHub. And if it works as well as the research paper claims, then problem solved. But I haven't actually got it working yet. So, anybody else?
Probably stop. 20 hours, right?
I never have a book.
Hopefully we'll see all the progress in another year or two.
Yeah.
All right, so that's it, everybody. Thank you, Doug. Thank you, Nathan. We have.
So, real quick, who here is a fan of FSF stuff? Free Software Foundation stuff? Who likes, like, gift certificates? Yeah, that group. Okay, that makes it difficult. Who wants a $25 gift certificate from the FSF Foundation? Okay, so maybe we'll fight it out to the death. I didn't expect so many hands. So, I don't know, discuss among.
What is a gift certificate? $25 for free software gets you all of the software?
Actually, maybe we should. That is, you want first refusal?
No, I think
Historical.
if it costs money, then I don't want it.
Yeah.
Um,
Well, it's FSF certified hardware, $25, stored on Vikings.net.